Good day, everyone. Today we will be conducting a virtual experiment on uniformly accelerated motion. Reminder before we proceed. You should have a copy of the activity sheet for this experiment, paper and pencil. Remember the instructions provided by your instructor or professor regarding this experiment. Hope you will acquire the expected learning from the experiment. In performing the activity, if you find the video too fast for you to grasp the instruction or the information given, or the task given like reading the measures of the data, you may pause the video until you're done. The objectives of this experiment are to study the motion of a body moving along an inclined plane, to calculate the uniform acceleration of the body from the obtained data, to determine the acceleration from the slope of the speed time graph. To obtain the measures of the quantities in this experiment, the following materials are needed: the meter stick, the jockey table, the inclined plane, the ticker tape timer or the recording timer, the toy cart, and the paper tape. Some background information important to this activity. Velocity is a speed with a specific direction. It seldom happens that the velocity of moving body is constant, since in most cases the velocity changes from time to time. Motion in which the velocity changes is called accelerated motion. Acceleration is the rate of change of velocity. As a formula or equation, average acceleration is the change in velocity divided by the change in time. When only the speed changes by a constant amount without a change in the direction of motion, the body is said to be undergoing uniformly accelerated motion. This figure illustrates the materials in this activity. Procedure number 1. Incline the plane using a small angle of inclination or as your instructor prescribes. Set up the rest of the materials as shown in the figure below. The paper tape is attached to one end of the cart and inserted between the clapper and the carbon paper disc. Procedure number 2. Start the timer and release the cart. Stop the cart as it reaches the lower end of the incline. Don't ever let the cart fall on the floor. At the same instant, turn off the timer. In the following video, observe how the experiment is performed.
This is the jockey table, and we have to raise the jockey table after the incline is placed on it. So raise the jockey table a little more than 15 degrees. Position the recording timer at the upper part of the incline and fix the position with a clamp to avoid motion during the experiment. This is the toy cart. In this toy cart, the paper tape will be attached so that when the toy cart moves down the plane, the paper tape will be pulled down together with the toy cart. So the toy cart and the paper tape have the same speed or motion. So we're going to use a carbon paper to make the dots more visible. Insert one end of the paper tape into the paper tape guide and let it pass through under the carbon paper. Now position the toy cart. Be ready with the release of the cart, and at the same time you have to press the recording timer. That's it. Now observe the paper tape. So the paper tape contains the dots, and observe the dots. So what happens to the dots as the cart moves down the plane? Compare the distances between the dots. So that paper tape will be for trial 1. Again, attach another paper tape to the toy cart for the second trial. Do the same as what you did for the first trial. Observe also the motion of the cart as it moves down the plane. There. That is our second trial. What can you say about the dots recorded on the paper tape?
After the experiment is performed, paper tape with record of dots like this one is obtained. On the paper tape, mark the first distinct dot and label it as 0. From the second dot, count off the dots on the paper tape and mark every fifth dot, 5, 10, 15, etc. Measure the total distance, TD, in centimeters, between the 0 mark and every succeeding mark, and enter your data in the second column of the table. Read the total distance using the meter stick or ruler. 0 to 5, 2.9 centimeters. 0 to 10, 6.3 centimeters. 0 to 15, 11.5 centimeters. 0 to 20, 17.5 centimeters. 0 to 25, 24.8 centimeters. From the paper tape for the data in this experiment, you have to count 55 dots and measure up to 0 to 55 dots. Step number 4. Calculate the distance traveled during each time interval. X. A time interval is equivalent to 5 dots by getting the difference between two successive total distances. In the table are the columns for the total time and the total distance measured earlier. Before this, determine the time interval. Time interval is the total time, column 1, divided by 5 dots. The third column in the table is for the time interval. Calculate the time interval as time sub 1 equals 5 divided by 5 dots equals 5 dots. Record on the table. Continue with the other time intervals. The fourth column is the distance traveled during its time interval in centimeters. Distance traveled during its time interval, x. Example, distance traveled x sub 1 is equal to the total distance of the first 5 dots. TD sub 5 minus 0. And distance traveled sub 1 is 2.9 centimeters. Record in the table. X sub 2 is equal to total distance of the 10 dots minus the total distance of the 5 dots, which is 6.3 centimeters minus 2.9 centimeters. The computed distance traveled during the second time interval is 3.4 centimeters. Record in the table. Distance traveled x sub 3 is equal to total distance sub 15 minus total distance sub 10. When computed, the distance traveled during the third time interval is 5.2 centimeters. Record in the table. Distance traveled x sub 4 is equal to total distance sub 20 minus total distance sub 15. When computed, the distance traveled during the third time interval is 6.0 centimeters. Record in the table. Continue finding the difference between the successive total distances to complete the 11 distance travels during each time interval. Step number 5. Calculate the average speed V sub average during each time interval in centimeter per dot by dividing the distance traveled during each time interval by 5 dots. The 5 dot counts constitutes a time interval in dots. The average speed is the distance traveled during each time interval, x, divided by 5 dots. Average velocity sub 1 is equal to 2.9 centimeters divided by 5 dots. Result is 0.58 centimeter per dot. Record in the column for the average speed. Average velocity sub 2 is equal to 3.4 centimeters divided by 5 dots. The result is 0.68 centimeter per dot. Record in the table. Continue calculating the average speed for the rest of the time intervals. Notice that the last column in the table is acceleration. Calculate the acceleration in centimeter per dot squared by dividing the difference between two successive speeds by 5 dots. Example, acceleration equals speed sub 2 minus speed sub 1 divided by 5 dots. Substitute the values for v sub 2 and v sub 1 from the table divided by 5 dots. The difference in velocities is 0.1 divided by 5 dots. The acceleration is 0.02 cm per dot square. Record in the table as the acceleration from v sub 1 to v sub 2. The next is example, the acceleration from v sub 2 to v sub 3. The acceleration is from the table 1.04 centimeters minus 0.68 centimeter divided by 5 dots. The answer is 0.072 centimeter per dot square. Record on the table. After calculating all the accelerations and completing the column for acceleration, calculate the average acceleration in centimeter per dot square for this trial. The average acceleration is equal to the sum of all accelerations, 1 to 10, divided by 10. Record the average acceleration on the table. All of these computations you have to do for the two trials in this experiment. The graphs of the relationships between variables in this experiment, you have to make 3 graphs for every trial in this experiment. The first graph is the total distance against total time. Trace a smooth curve. The suggested format, the graph of total distance traveled against the total time of travel. Describe the suggested relationship based on the graph line between the total distance and the total time. Plot average speed during each time interval against the midpoint of the time interval. Draw the average straight line. Determine the slope of the line. Compare the slope with the computed average acceleration and determine the percentage difference. The suggested format for the graph of average speed and midpoint of the time interval. Compute the slope of the graph line of average speed and midpoint of time interval using the slope formula. Calculate the percentage difference by dividing the difference between slope and computed average acceleration by the average of the slope and computed average acceleration times 100%. The third graph. Plot the acceleration against the time interval. Approximate the best graph from the plotted points. The suggested axis for the graph of the acceleration and time interval. Describe the graph line of acceleration and time interval. Compare the value of the acceleration of the best graph of the plotted points to the computed average acceleration. From the data measured and computed, these tables will be used for trial 1 and trial 2. Compute the average acceleration for each trial afterwards. The data for this experiment. For trial 1, this is the paper tape with recorded dots. The first clear dot is counted as 0. The succeeding dots, count and mark every 5 dots. The 0, 5, 10, 15, 20, 25, 35, 40, 45, 50, and 55. Measure the total distance from 0 dot using the meter stick or a ruler. Read the measure from the meter stick and record as the total distance. Should you need more time in reading the measures, pause this video. Don't forget to play again to continue in this experiment. For trial 2, this is the paper tape with recorded dots. The first clear dot is counted as 0. The succeeding dots, count and mark every 5 dots. 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, and 55. Measure the total distance from 0 using the ruler or meter stick. Read the measure from the meter stick and record as the total distance. The same as the trial 1. If you need more time in reading the measures, pause this video. But don't forget to play again to continue in this experiment. For additional instructions in this experiment, record data on the table in the activity sheets provided. Compute the time interval, distance traveled during its time interval, average speed, acceleration, and average acceleration. Show the necessary computations. Draw the graphs. Answer the questions provided. Complete the report and submit to your instruction. Before ending this virtual experiment, the author would like to acknowledge the entire physics department. This virtual experiment was adapted from the laboratory manual developed by the department, converted to this format to suit the present situation that calls for online or virtual classes. The video in this presentation was taken from the videos prepared by the following physics faculty: Professor Nelson M. Abana, Head, Professor Danilo Violete, and Professor Richard L. Muhi. Hope this video had helped you attain the objectives for this experiment in uniformly accelerated motion. Thank you for watching this video.